Okay, so logistic growth and partial fractions. We're going to start off understanding what logistic growth means, and then we're going to look at partial fractions because you need to know partial fractions in order to do logistic growth. So first of all, what is logistic growth? So many things that grow exponentially cannot continue to do so indefinitely in real life. So you've looked at exponential functions, correct? Exponential functions, they all start off somewhere and then they just keep on growing forever and ever. Basically, the idea here is for an exponential function is that the sum with respect to time is directly proportional to y. So as y is growing, so is the sum. Okay? Now, logistically speaking, in real life, things cannot grow exponentially. For example, population. Okay? After a while, things that start off growing exponentially begin to compete for resources like food, water, money, parking spaces. So the growth begins to taper off as it approaches some carrying capacity of that system. So, logistically speaking, in this case, the growth rate is not only proportional to the current value, so it is proportional to the current value, the growth rate, okay, proportional to the current value, but also how far the current value is from the carrying capacity. All right, so here's the best way to kind of explain it. Imagine a rumor spreading throughout the school of 2,000 students, okay? The rate of which the rumor spreads is directly proportional to both the students who have heard the rumor and the students who have yet to hear the rumor, as the number of people hearing the rumor approaches 2,000. Now, logistically speaking, when the rumor reaches its max, where it can no longer grow, is once it's reached 2,000. So the idea is we call this y value L. Basically, this is its capacity, okay? Its limit to growth. Now, the way that we have to think about this is the rumor starts growing pretty quick, okay? So at first, the growth rate is only proportional to how many students are hearing it. Now, eventually, once it gets to this point right here, let's mark it right over here. So once it gets to this point right here, which in terms of the whole entire graph, this is the halfway mark. So if there's 2,000 students, we'll call this one, and I probably should have made it more around here just so you can see it, but here y equals L over 2. Okay, so basically as soon as 1,000 people hear the rumor, then it stops growing exponentially and we actually end up with a change in the exponential growth and it starts to taper off. And if you remember, second derivative, this is the inflection point or inflection point. It's when it changes from concave up and then all of a sudden it becomes a concave down graph. Okay, so the idea is, best way to explain it is that logistically speaking, the limit as time grows to infinity, so the longer that the rumor is being spread, it is going to reach an end behavior or a max of L. This is its limit to growth or its capacity, its carrying capacity. Okay, so the thing is if you look at this, the graph right here, from here to here, is your y portion of the graph. So at each one of these points, you're getting a y value, okay? But if you look at the graph from here to here, this is actually how close you are getting to your limit capacity. So it's your L. So logistically speaking, the derivative of y with respect to time is similar to the exponential because it does start where k is going to be directly proportional to y, okay? So the growth rate is going to be directly proportional to its current value. So if 5 people know, it's going to continue growing, 10 people, 100 people, 1,000 people. But it's also going to be directly proportional to the carrying capacity minus the current value of y. Okay, so this is really the important equation that we are going to get from all of this. So logistic growth just means that exponential functions cannot grow to infinity. Eventually, as they approach infinity, they are going to always reach a carrying capacity in real life. Population, if it grows infinitely, the world is not going to be able to hold it. At some point, there's not going to be enough food, there's not going to be enough resources and other things, so the population is going to reach its carrying capacity and stop growing. So for quantities y, this is what this graph is telling us. For quantities y that grow logistically with a carrying capacity of y equals L, we can state the relation mathematically the following way, that the derivative of y with respect to time is equal to some constant k times y, directly proportional, times the carrying capacity, which is L, minus that y value. Okay, now you've seen these before. So the idea of solving this for y is kind of like an initial value problem, right? You need to first separate your y's and your t's so that you're able to integrate. So remember, the idea is get the y's together, and then the dt is going to be left over with the constants. Now this right here is our constant, okay? L is going to be your carrying capacity, but you don't really know what L is. I mean, it is going to end up being a constant, but it does have to stay with y because it is dependent on y. So if we try to separate these, first you would multiply both sides by dt. So you'd end up with dy equals ky L minus y dt, and then to get y times L minus y with the y's. So y times L minus y, you divide both sides by y minus L minus y, y times. So that cancels out on this side. So you're left with, let's write it right here, you're left with dy over y times L minus y equals k times dt. And then of course, now that we've separated as much as possible, I know that just keep in mind that k is really just a number, okay? It's a constant. So now we can integrate both sides. So integrating this side is easy. The integral of a number is that number times t plus c on this side. Now on this side, if we wanted to integrate it, we still don't really know how to do this. So another way that we can look at this problem is, what if I asked you to integrate 1 over x times 4 minus x dx? Can we integrate this? basically you would think first of u substitution. Now keep in mind that this is 1 over 4x minus x squared. So if you thought of u substitution, you would end up with u being 4 minus x squared, so du is going to be negative 2x, which you can't do because you don't have an x in that numerator. You can't use really integration by parts because, again, if u is 4 minus x squared, then you're basically breaking up that fraction, and we can't do that. With integration by parts, you have to have two functions that are multiplied together. So your u would actually have to be 1 over 4 minus x squared. So we don't yet know how to do this. Okay, so right now we can't integrate it, but there is a way. So solving this differential equation requires a new integration technique called integration by partial fraction decomposition. All right, so we do have an easy way to do this. So we're going to pull away a little bit from logistic growth, and we're going to review what integration by partial fraction decomposition is. All right, so here's example 1. Example 1 says add then simplify by finding a common denominator. Looks familiar? Okay, rational function. How do we simplify this rational function? What do we need to find? Okay, you said a least common denominator. Very good. So we need to find an LCD. And what is the LCD of 2x minus 1 times x and x minus 3? It's their product. So that means, what do I have to do on this side of the equation? I need to multiply the top and the bottom by x minus 3. And then on this side of the equation, I need to multiply the top and the bottom by 2x minus 1, because I need to get a common denominator in both of these parts. So we multiply this out, so this is 5 times x minus 3 minus 2 times 2x minus 1, and then all of that is going to be over x minus 3 times 2x minus 1. Now we got a common denominator. So we finish cleaning this up, and this ends up being 5x minus 15 minus 2x plus 1, all of that over, let's simplify this. So this ends up being 2x squared, outer is minus x, inner is minus 6x, so we got minus 7x plus 3. Let's continue cleaning this up. So we got 5x minus 2x, which is 3x, and negative 15 plus 1 is going to be negative 14. And all of that is going to be over 2x squared minus 7x plus 3. Oh, I made a little mistake. 2 times 2x is 4x, so this is actually going to be x minus 14. X minus, oh my god, I completely forgot to distribute that too. Sorry. It is 10:30, so I'm a little tired. Alright, so this is x minus 13 over 2x squared minus 7x plus 1. So you remember how to do this method, okay? Integration by parts is basically, I'm going to rewrite this just because it's looking ugly. Integration by parts is basically taking a problem that looks like this. You cannot, and integrating it. Okay, so let's look at this problem right here. This problem is telling us to integrate x minus 13 over 2x squared minus 7x plus 3. So of course your first try is you want to integrate this using maybe u substitution. Okay, you can't use integration by parts because it is one function. It's not two separate multiplied functions. So you want to use u substitution, but you notice that if u is 2x squared minus 7x plus 3, then du is going to be 4x minus 7. And then here, you don't have, there's no way that you can factor that out to make it work for x minus 13. Okay? You can try, and then you can let me know what you get, but you can't do it. So the idea is that we want to break this up. Okay? We want to break this up and into two separate linear fractions so that we can actually integrate it using ln. So now, because we just did this problem, it's easy to see that x minus 13 over 2x squared minus 7x plus 3 is equal to the integral of 5 over 2x minus 1 minus 2 over x minus 3 dx. Right? We just did that. So if this equals this, then that means this rational functions equal these two individual rational functions. And now this becomes easy to integrate because you can separate, because there's a minus, so we can separate this into two separate integrals. 5 over 2x minus 1 minus the integral of 2 over x minus 3 dx. And then we can integrate. First thing we do is pull out the constants, so that 5 comes along for the ride. And this is 1 over 2x minus 1 minus the 2 comes out, 1 over x minus 3. And we can integrate using u substitution. Now you'll notice, and I hope you've already noticed, is that anytime that you have a linear factor in the denominator and you use u substitution, basically you're going to end up integrating 1 over u. Okay, but keep in mind that we do still have to take into account that if you use u substitution, so let's actually do a little side work of u sub. So u sub, let's let u equal 2x minus 1. So du is going to be equal to 2 dx. But of course we wanted it to equal 1 dx, so we're going to divide both sides by 2. So now if I rewrite this side, it's going to be the integral of 1 over u times du over 2 minus the same thing here. I'm going to do a side work of u sub. And I'm going to let u equal x minus 3. So du is going to actually equal dx. So that cleans up a little bit nicer. So we have a 2 here, and that's going to be the integral of 1 over u du. Keep in mind that this u and this u are different, so actually what we should probably do is call this a v sub. Okay, so call this v dv, just so that we don't confuse that this u is right here and this is right here. So now we continue integrating, so we get 5, pull out the 1/2, so this is 5/2, and what's the integral of 1 over u? Ln of the absolute value of u, minus 2, the integral of 1 over v is ln of the absolute value of v, don't forget the plus c. And now we just plug in. What's our u? It was 2x minus 1. And what's our v? It was x minus 3 plus c. Now we're basically done. Just keep in mind that this is natural logs, and on the AP exam what they could do is, rewrite the problem. Remember that this is, they can basically use the power rule and bring the coefficient that's in front of the ln and make it an exponent for both of these. So you could also end up with ln, the absolute value of 2x minus 1 to the 5 halves, minus ln of x minus 3 squared plus c. So that's another possibility that the answer can look like. Now on our quizzes, if it's free response, you can keep it like that. Just know that these two are the same. Okay? But this was easy because you really didn't have to do much work. The work really comes from breaking up this rational function into two individual linear, non-repeating, okay, they can't be the same, so non-repeating denominators, okay? So in order to do that, we actually do have a method. So on the AP exam, you're going to be expected to decompose the rational expression involving non-repeating linear factors, key, non-repeating, they have to be linear factors in the denominator. You're not going to have an example like example 1 that we just did where it shows you the pre and then you start off with the integration. So for cases as this one, there is a very slick method that you can use. It was developed by Oliver, not so much on the Heaviside, so his name is Oliver Heaviside. It's called the Heaviside cover-up method. I'm just going to call it the cover-up method. But here's an example. We'll do under the watchful eye of Mr. Heaviside. You can tell that I got this from someone else's notes, so it's not what I would normally say. So we're going to use the cover-up method. So here's our example. So what's our goal? Basically, our goal is we want to first, step 1, factor the denominator. Okay, so when you first factor the denominator, you end up with x plus 5 over, our two factors are going to be two numbers that multiply to -2, add up to 1, so that's going to be x plus 2 times x minus 1. So the reason why we are able to use this method is because we have two non-repeating linear factors. Okay, there are two non-repeating linear factors. So we're going to use the partial fractions. And there is also one more thing that we have to watch for, why partial fractions does work. And this is because, if you remember Bobo Batten eats DC, this is bigger on the bottom. So partial fractions only works with rational functions that are bigger on the bottom. Okay? If it's bigger on the top, we're going to actually end up dividing first and then using partial fractions if we needed to, and we have an example in here where we're going to do that. Okay, so now that you have your denominators, what we want to do now is basically split this up. So we want to split this up into two linear factors, two linear rationals. One with x plus 2 as the denominator, one with x minus 1 as the denominator. Now the question is what is the numerator? So once you have your factors in the denominator, this is where the cover-up method comes into play. You pick a factor, pick one factor, and set it equal to 0. So I'm just going to pick x plus 2. So x plus 2 equals 0. So where does x plus 2 equal 0? When x equals -2. So the way that the cover-up method works is because you started with x plus 2, that's what you're going to cover up. So I'm going to cover up x plus 2. And then I'm going to take this x equals negative 2. Okay, so I'm going to cover up x plus 2. And then I'm going to plug in x equals negative 2 to what's left. So here, negative 2 plus 5 over negative 2 minus 1. And what we're left with is negative 3 over negative 3, which is positive 1. And guess what? That's your numerator for x plus 2. Okay? You're going to do the same thing for the second guy. So, pick the second factor. X minus 1 equals 0. Where does it equal 0? At x equals 1. So I'm going to cover up my x minus 1 factor, and I'm going to plug in x equals 1 to what's left. So 1 plus 5 over 1 plus 2, which is 6 over 3, and that's 2. And that right there is my denominator, my numerator for x minus 1. And since it's a positive, that will give me the middle sign of positive. If this was a negative, then that would be a negative. If it's a positive, so it's a positive. Dx. Okay? And you can check your work. Okay? You can always check to make sure that you are correct. And the easiest way to check is basically the crisscross. Okay? Cross multiply. So if we cross multiply, we get x minus 1 negative 2 plus 5 is positive 3. I made a mistake again. That's supposed to be negative 1. That's supposed to be a negative 1. So negative 1 times x minus 1 plus 2 times x plus 2, all of that over x plus 2 over x minus 1. Clean this up, and what do we get? You get negative x plus 1 plus 2x plus 4, all of that over x plus 2, x minus 1. Continue cleaning this up, so you get negative x plus 2x, which is x. 1 plus 4 is 5, all of that over x squared plus x minus 2. So does that answer look like the original? Absolutely it does. So you know that you've actually broken this down or decomposed this function correctly. And now the rest is easy. Okay, I'm going to break up my integrals and I'm going to pull out the coefficients. So that's going to be a negative, and we're left with 1 over x plus 2, plus, pull out the 2, the integral of 1 over x minus 1. Now, when there's a 1 on top, this is extremely easy. It's 1 over, if I use u substitution, it's going to be u. So, and then du is just going to be dx. Okay? So the idea is that this is negative. The integral of 1 over x plus 2 is ln, absolute value of x plus 2, plus 2 ln, because it's 1 over a linear function, ln of x minus 1 plus c. Okay, and that's my answer. Done. Now, if you wanted to bring up that squared and get rid of the absolute value, you can, absolutely. Alright. Alright, so we're already at 29 minutes. And we haven't even gone back to the logistic growth problem. So just really quick, I guess I'll finish this off. In order for partial fraction decomposition to work, the degree of the denominator must be greater than that of the numerator. So Bobo has to apply. Okay, it has to be bigger on the bottom. When it's not, we'll use our tried and true method of long division first. And you guys better remember long division. So here's our example. Okay, this is bigger on top. So if it's bigger on top, we're going to divide first. So if you remember with division, you take x squared minus 1 and you divide it by 3x to the 4th, and then you put some place values. I mean, if you don't really have to, if you remember to place things in the correct spot, I like to put place values. So 3x to the 4th divided by x squared is going to give us 3x squared. Multiply that out, so that's going to be 3x to the 4th minus 3x squared. I'm going to put it right here. Put them in parentheses and subtract. That cancels out, and then 0 minus negative is going to give us 3x squared, and then everything comes down. Next up, 3x squared divided by x squared is plus 3. Multiply 3x squared minus 3. Parentheses and subtract. That cancels out, and then 1 minus negative 3 is going to be 4. That's our remainder. And remember, how do we rewrite our remainder? 4 over whatever your divisor was. So basically, what we can do now is we can rewrite this problem using our quotient. Okay, so our new integral that we have to take is going to be the integral of 3x squared plus 3, but you can't forget about the remainder, plus 4 over x squared minus 1. Okay? Because this is addition, so we can use, we can separate these integrals, all 3 of them, and integrate these easy ones first. So this is 3x squared integral plus the integral of 3 plus the integral of 4 over x squared minus 1. Now these two integrate perfectly. The integral of 3x squared is easy. It's going to be 3x cubed over 3, which is x cubed, plus the integral of 3 is easy. It's just going to be 3x to the 1 over 1. Now this one, we're going to have to use the cover-up method. This is bigger on the bottom, and there's no way to use u substitution, because if u is x squared and then du is 2x, you can't do that. If this was plus 1 over here, we could actually use the inverse trig, right? The integral of 1 over x squared minus 1, x squared plus 1. But it's not, it's minus, so it has nothing to do with trig. So we're going to actually factor the denominator, and this factors out perfectly into x plus 1, x minus 1, and you're going to use the cover-up method in order to do what? So I'm going to go here. I'm going to bring along the x squared plus 3x for every single step. So the idea is you want to break this up into 2 linear, non-repeating denominators. One is x plus 1, the other one's x minus 1. The question is what is our numerators? Maybe you guys can figure this out. I'm going to stop the video and we'll come back to the very fun problem of integrating this differential equation and solving for y. All right, good luck. And if you did want to do some partial fraction problems, just look up some stuff look up partial fraction integration on the internet, or if you've already bought your review books, go to partial fractions. They have a lot of review problems. Good luck.